All right, here's my video guide for lesson 10.2.3, the last lesson that we really do with probability in here. And really, it's just going to bring everything together that we've talked about: conditional probability, two-way tables, your standard probability, your area models. We're going to see it all here. This is a little bit longer of a lesson, but I've shrunk it down to 3 problems. And it's just really 3 problems I chose, not really any specific order to them, but I kind of wanted to choose 3 that hit everything that we've seen in 10.2.1, 10.2.2, and now 10.2.3. And with that said, we'll get into the first one here. And this is just going to be a problem where we work with a two-way table. So it says, in a recent survey of college freshmen, 35% of students check the box next to exercise regularly. 33% check the box next to eat 5 servings of fruit and vegetables a day, and 57% check the box next to neither. And so this might remind you of a problem that we did yesterday with the two-way table, and we're going to do it again here now. And so we're going to do part A. I already have a setup of the two-way table here, and so I'm going to flip back and forth. And so we have exercise and no exercise, and we have fruit and no fruit. Exercise meaning that they are regularly exercising, no exercise meaning they're not, and then fruit means they're eating 5 servings of fruit, and no fruit means that they're not doing that. All right, and really what we're doing here is we're going to take these percentages and we're going to write them as decimals so we can work with them. All right, and that's kind of my first part here. And we're going to start with 35% of students check the box next to exercise regularly. And so what I'm going to do, and this is kind of what we did in our two-way table yesterday, is I'm going to say exercise will 0.35, because that's 35% in a decimal, are exercising. But I can't put them in the two-way table yet because I don't know if that 35% is eating fruit or not eating fruit. So I'm just saying I know 35% are exercising. All right? And the next thing I'm going to do then is say then 33% check the box next to eating 5 servings of fruits. You're eating 5 servings of fruits and vegetables a day. So I'm going to go from fruit and put 0.33 down here because, again, I don't know if those people are exercising or not exercising, but I do know they're eating fruit. I know that 33% of people are eating fruit. All right, and then the last one, we have 57% check the box next to neither, meaning they're not eating fruit and they're not working out. And actually, that is a box in here. And so I put a 0.57, a 0.57 in this box because they are not exercising and they're not eating fruit. All right. Because these are percentages and percentages are always out of 100, that means 35% are exercising, and that means 65% is not exercising because that has to get up to 100%, or in this case, because it's a decimal, has to get up to 1. With that too, we can say the same thing for no fruit, because we know 33% of people are eating fruit. That means 67% are not eating fruit, because we again need to get up to that 100%, or that in the case of a decimal 1. And now that we know these here, we can fill out the rest of the two-way table with our percentages. All right, since this is 0.57, that means right here we'd have to have 0.1 or 0.10, because 0.10 plus 0.57 gives you your 0.67 down here, which would be our total of no fruit. Because this one is 0.10, that means this one here has to be 0.25, because 0.25 plus 0.10 gives you your 0.35 here. And if that one's 0.25, this one has to be 0.08, because 0.08 plus this gives me my 33%. And all of a sudden we have our two-way table. And so we have exercise and eat fruit. That's 25% of people. Eating fruit with no exercise is 8% of people. No fruit, no exercise is 57% of people. And exercise with no fruit is 10% of people. And really just based off the idea that I knew these had to go to 100% on the sides, and then we can fill out our table knowing what our totals had to be. Okay, now we can start answering questions using the two-way table. And so for part B, it says, what is the probability that a freshman in this study exercises regularly and eats 5 servings of fruit a day? And so we're going to look at exercising and fruit, and we're going to say for part B here, part B, 25% of those students, because of this box right here, exercise and eating fruit is 25% or 0.25, and that's really what this question's asking, is exercising and eating fruit. And so I just choose that 0.25 and say 25% of students are exercising and eating fruit. All right, and then in part C, it says, what is the probability that a freshman in this study exercises regularly or eats 5 servings of fruit a day? So we can do exercising or eating, which is just going to be this idea of the addition of the two. We can say, well, we'll take the number of people exercising and add the people eating fruit because it's one or the other. So in part C here, we have 25% of the people are exercising and eating fruit. We have 0.08 people. It's really going to be these. I can kind of highlight it here. It's really going to be this box because there's exercise and fruit. This one here also counts because there's fruit. And this one here also counts because there's exercise. And it's an and or thing, so we can choose them all. So I'm going to take all 3 of these highlighted boxes here, and I'm going to add them together to get my probability here. And so 0.25 plus 0.08 plus the last one was 0.10. And that will give me, if I add them all up, this becomes 33, this becomes 0.43, or 43% of the people, or of these freshmen studied, 43% of them are eating fruit or exercising, or doing both technically. All right. Moving on to D, we get to do a little bit of independence here, or association. So it says, do you think freshmen who eat 5 servings of fruit and vegetables per day are more likely to exercise? In other words, are exercising and eating associated? And remember, the way that we show if 2 things are associated is just to show, are they independent or not independent? Meaning, if their probability without something given is the same with it given, that would be independent of one another. If they are different probabilities, that means they would just be associated to one another. So what we're going to do is we're going to take the probability of exercising, and then we're going to do the probability of exercising given that we know they're eating fruit, and we're going to see if those 2 probabilities are the same, because if they're the same, then they must be independent. Okay, so D, the probability of exercising, we have 35% are exercising, and so we say the probability of exercising is 35%. Probability of X, and I'm just going to say that because I don't want to write out exercise, is equal to 35%. Now, what about the probability of exercising given fruit? I'm just going to put an F for fruit. All right. Remember this, how this is always changes, because now that we're given fruit, and I'm going to use my highlighter again, different color this time. Now that we're given fruit, our sample size changed. We're just going to focus on this and this, which means our new sample space is really out of 0.33 and not out of 100. And then we're talking about exercising, eating fruit, and so we're going to take, we're going to make our fraction on the bottom is our sample space, or our entire sample, which is 0.33. And then we're just choosing the one where we're talking about exercising and fruit on top, and we get 0.25, 0.25 on top, because again, that 33 from the bottom, or that 33 on bottom, is coming from, we know it has to be some kind of fruit, and so that there's 0.33% of people are eating fruit, so that's the total amount of people. And then that 0.25 are the people that are exercising and eating fruit, and that's how we do our conditional probability. And so if I actually calculate this to get a percent to see if it's the same as 35%, I will do 0.25 divided by 0.33, and that actually gives me about, I should use my about one, 76% of people are exercising, given that you know they're eating fruit. So that's very different probabilities. Those are not equal, and since they're not equal, we can say that they are associated. Okay, Now the last part, compare and contrast the two-way model and the area model. Now I'm not going to write anything down because I kind of want you to just kind of look at this and see how it's different. But a couple things that I noticed right away that are kind of similar is we are writing, this is usually on a area model, we'll write a fraction that goes with no fruit or fruit, and we'll multiply in to find this. In this case, we have the totals out here, and we use the totals to find what goes on the inside instead of just multiplying in like we would with an area model. But there's a lot of things that are different or actually pretty similar here, so I'm going to let you kind of choose what you want to write. It doesn't have to be anything specific, just point out some things you notice that might be the same or different. Okay, we'll move on to 93 here, and actually a problem we did back in chapter 4. And so it says, remember the double spin game from chapter 4, there it is. The player gets to spin the spinner twice, but only wins if the same amount comes up both times, meaning you'd have to spin 100 the first time and then 100 again the second time to win the $100. It says for our reference that the $100 sector is 1/8 of the circle, and Nick is currently playing the game. So what it wants us to do is make an area model to show the sample space of every possible outcome for the two spins, and we want to figure out what the probability is that Nick wins. And so I actually have one kind of being made right here. We have 100, 10, 5, 1 from spin 1 over here, and then 100, 10, 5, 1 from spin 2 on top. I got to fill in the probabilities here though. If you were to get 100, you have a 1/8 chance to get 100 on both spins, which means you have, if I look at this, if 100 here is 1/8, then the 1 must be 3/8, because 3/8 plus 1/8 gives you 4/8, which would be half the circle, 4/8 being half the circle. And so I can say my probability for getting a 10 is 3/8, and the 10 up here would also be 3/8. If I go back to my table, or my circle here, the 5 is a 1/4 chance, and the 10 is a 1/4 chance because this is clearly 1/4 of a circle for each of them. And so for a 5 you get 1/4, and for a 1 you get 1/4. And you can say the same for the second spin as well. Alright, and I'm going to do a little pausing here, and I'm going to fill out my table. Remember what I'm going to be doing here is just multiplying in. So if I'm talking about the square that goes with 100, I'm multiplying 1/8 times 1/8 to fill in this circle like I would do with any area model. The table is filled out. Like I said, I just multiplied the fractions to get what goes in the box. And to answer the question for part A, it says, what is the probability that Nick wins? Well, Nick wins down this diagonal because Nick wins if he gets 100 and 100, 10 and a 10, 5 and a 5, and a 1 and a 1. So what we're going to do is we're going to add the probabilities of this diagonal to figure out the total probability that he could win. So we're going to do, I might do a little editing magic here again and do some work behind the scenes, but really what it is, adding that diagonal, 1/64 plus 9/64 plus 1/16 plus 1/16. All those are added together because those are all the chances we have to win. We're going to need a common denominator. Luckily, these will go down to be our common denominator here, and we'll have a common denominator of something over 64. So 1/64 plus 9/64. To get 16 to be 64, we got to multiply it by 4. So if we multiply that whole fraction by 4, it becomes 4/64 plus another 4/64. And now we could actually add them. The denominator, of course, is going to be 64. And then adding the tops, 1 plus 9 is 10, 10 plus 4 is 14, 14 plus 4 is 18. So we get 18 out of 64 here. The probability that Nick wins is that 18/64, or if we wanted to put that in terms of a percentage, that would be he has a 28% chance to win. All right, I'm going to end this video here. We will finish B, C, and D, and this last problem, actually 96 is the last problem. We'll finish that in the second video.